Gravitational waves carry energy. Consider two freely falling test masses. These test masses follow time-like geodesics in the spacetime. As a gravitational wave passes, it causes space to expand and contract in directions perpendicular to the direction of propagation. This expansion and contraction causes the separation between these masses to vary. These oscillating masses have kinetic energy, and we can capture some of this energy by letting the masses slide along a rigid rod. So this is the rigid rod. And as the masses oscillate, friction between the masses and the rod will generate thermal energy. In other words, the temperature of the masses in the rod will increase. By the way, in case you haven't thought about this, let me point out that the rod itself will not expand and contract along with space as the gravitational wave passes by, at least not by very much. The atoms in the rod are pretty much locked in place due to interatomic forces, so the length of the rod is fixed. Of course, it's not completely fixed. There's no such thing as a rigid rod. But we can imagine that the rod is very stiff, so that its expansion and contraction is negligible compared to the motion of the test masses. This thought experiment, which is often credited to Feynman, first appeared in the late 1950s, and it was used to help convince the gravitational wave doubters that gravitational waves are real. They carry energy, and they can produce real physical effects. How do we identify and quantify the energy in a gravitational wave? To answer that, we must address the role that energy plays in general relativity. Energy produces space-time curvature. In particular, gravitational waves must produce space-time curvature. Does this make sense? After all, the gravitational wave is itself a part of the space-time geometry that it's supposed to be curving. To explain how this can happen, we need to look more closely at the mathematical description of gravitational waves. Recall, in the previous lectures, we wrote the space-time metric g mu nu as a flat background, eta mu nu, plus a perturbation, h mu nu. So eta is the flat background, and h is the perturbation, which contains the gravitational waves. The equations of motion that govern the perturbations are the linearized Einstein equations. We derived those equations in the previous lecture by first expanding the Einstein tensor, which depends on the metric g, but the metric g can be written as eta plus h, and we expanded this in a series for small h. So the first term is just g mu nu of eta. The second term is linear in h, so we call that gl. It depends on eta and h. The next term is quadratic in the perturbation, so we call that gq. And of course there are higher order terms. We also considered the expansion of the stress energy momentum tensor for the matter fields. So this depends on the metric as well as matter fields. So this is T mu nu of eta plus h, which in the expansion becomes T mu nu of eta plus a linear term in h plus quadratic and higher order terms. Since the background metric is flat, of course g mu nu of eta vanishes. So the leading order term in the Einstein tensor is this linear term in h. And if we assume that the matter fields are small, then the leading order term in T mu nu is also of order 1 in smallness, and it's this term T mu nu of eta. So the linearized Einstein equations are g mu nu L of eta into h equals 8 pi times T mu nu of eta. Now let's return to the question at hand. What does it mean for a gravitational wave to produce space-time curvature? The answer is that the gravitational wave causes the background to become curved, so the background is no longer flat. So we see that in order to account for the energy in a gravitational wave, we must allow for the background to become curved. In other words, we need to generalize our mathematical analysis and write the space-time metric as g mu nu equals a general background, which we'll call g tilde mu nu, plus a perturbation h mu nu. So g tilde is the background metric. It's possibly curved. And h mu nu is the small perturbation. Of course, in practice, the background metric might be very close to the flat metric, but for now we must allow for some small curvature if we want to self-consistently define the energy of a gravitational wave. The first thing we need to do is to repeat our calculations of the series expansions for the Einstein tensor and the stress energy momentum tensor. So the Einstein tensor, g mu nu, depends on the metric g. That's g mu nu of g tilde plus the perturbation h. We expand that as g mu nu of g tilde, that's the Einstein tensor for the background metric, plus a term gl that's linear in the perturbation. It depends on the background as well as the perturbation, plus a term that's quadratic in the perturbation, and so forth. And of course we can carry out the same expansion for the stress energy momentum tensor. So this is T mu nu of the background metric plus linear terms and so forth. Of course, one immediate difference we have between this case and the case in which the background metric was flat is that this leading order term in the Einstein tensor is not necessarily zero. Let's go ahead and write out the Einstein equations. We have g mu nu of g tilde plus the linear terms plus the quadratic terms, and then there are higher order terms. That's equal to 8 pi times the stress energy momentum tensor. That's T mu nu of G tilde plus linear terms, and so forth. Now we're going to drop these higher order terms, which are cubic and higher in the perturbation h. And also, to keep the notation from being too cluttered, let's just go back to the original notation and call this combination T mu nu of G. And the Einstein equations become G mu nu of G tilde plus the linear terms. And now the quadratic terms I'm going to bring to the right-hand side and write in the following way. This is 8 pi times T mu nu of G. That's all of the right-hand side here. And then these quadratic terms will write as minus 1 over 8 pi times G quadratic mu nu of G tilde and H. Now, in writing the Einstein equations in this way, it suggests that we can interpret these quadratic terms as a stress energy momentum tensor for the gravitational waves. But that's not quite correct. So before we jump to this conclusion, we need to be careful. We need to address a fundamental question. And that is, how do we distinguish between the background and the perturbation? After all, there's just one metric, G mu nu, and we've somehow split it into two pieces, a large piece which we call the background, G tilde, and a small piece which we call the perturbation, H mu nu. But we could always take part of the perturbation H, take it away, and put it into the background G tilde. Or the other way around, we could take a small amount of the background away from G tilde and place it into H. So how do we define this separation? Well, in general, we can't. But one situation in which we can define this separation is when the variations in the metric occur on two widely separated length or time scales. So let's assume that the metric varies on two widely separated length or time scales. In this case, we define the background metric, G tilde, to be the long wavelength, or low frequency part of the metric, and the perturbation H is the short wavelength, or high frequency part. Let me draw a picture. This represents the full metric, G mu nu. As you can see, the metric has variations on long length scales and also on short length scales. So we define the background as the long wavelength part. This is G tilde mu nu, and the perturbation as the short wavelength part. So this is H mu nu. And of course the full metric is equal to the background metric plus the perturbation. An example in which we naturally think in terms of this separation between background and perturbation is the ocean. The height of the water has a long wavelength, low frequency part. These are the tides due to motion of the Earth, Moon, and Sun. The height of the water also has a short wavelength, high frequency part. These are the surface waves, due mostly to the wind. And notice these scales are widely separated. The tides occur on a length scale of thousands of kilometers, whereas the surface waves occur on a length scale of meters or tens of meters. This separation in scales allows us to naturally split the height of the water into a background and perturbation. Now let's return to our examination of the energy in gravitational waves. So we assume that the metric can be cleanly separated into a low-frequency background and a high-frequency perturbation. Now let me write down our previous result for the Einstein equations expanded to quadratic order in the perturbation. We have the Einstein tensor of the background plus the linearized Einstein tensor, which depends on the background and depends linearly on the perturbation h, equals 8 pi times the stress energy momentum tensor minus 1 over 8 pi times the quadratic terms in the expansion of the Einstein tensor. Now, there's not a lot that we can say about this term, T mu nu, unless we specify more details about the matter fields. But let's focus on these other terms, these three terms, the big G terms. Each one of these is built from nonlinear combinations of the background metric G tilde and the perturbation H. In particular, the Einstein tensor for the background metric is built from nonlinear combinations of low frequency components. So this is combinations of low frequencies. Now this term GL is built from the background metric, and each term is linear in H. So it's built from low frequencies contained in G tilde plus a linear factor of high frequency. So one factor in each term with high frequency. And now GQ, because it's quadratic in H, it contains low frequencies from G tilde plus two factors in each term with high frequency. So what happens when we take nonlinear combinations of factors with different frequencies? Well, let's just take a look at a simple example. Consider the product of two sine functions with different frequencies, omega 1 and omega 2. This is proportional to cosine of omega 1 plus omega 2 times t plus cosine of omega 1 minus omega 2 times t. So this nonlinear combination gives us two terms, one with frequency omega 1 plus omega 2, the other with frequency omega 1 minus omega 2. So what happens if both omega 1 and omega 2 are low frequency? Omega 1 and omega 2 are both small. That means omega 1 plus omega 2 is small, omega 1 minus omega 2 is small. So this combination just gives low frequencies. So let's make a little chart here. If omega 1 and omega 2 are both low frequency, then the result on the right hand side is just low frequency terms. Now what if one of these, say omega 1 is low frequency and omega 2 is high frequency? Then this combination is high frequency because omega 2 is large. Omega 2 is large here, so this is also high frequency. So this just gives us high frequency results. And now let's assume that both omega 1 and omega 2 are high frequency. So both omega 1 and omega 2 are large numbers. That means omega 1 plus omega 2 will be a large number and give us a high frequency term, but omega 1 minus omega 2 can be a small number, so this can be a low frequency term. So the result here is both high and low frequencies. So keeping these results in mind, let's go back and examine the Einstein equations. We have this first term is just a combination of low frequencies, which will always give us just low frequencies. These terms in the linear Einstein tensor are combinations of low frequencies and just one high frequency, which always gives us a high frequency. This term, the quadratic terms in H, have two factors of high frequencies in each term, so they can give us both low and high frequencies. And of course, the matter terms, depending on their details, could give us low or high frequencies. So we can see from this analysis that the Einstein equations can be split into two equations, a low frequency part and a high frequency part. The low frequency equation is just the Einstein tensor evaluated on the background metric equal to the low frequency parts of t mu nu and quadratic g. The high frequency equation is the linear Einstein tensor set equal to the high frequency parts of the right hand side. So let's write those equations as follows. We have the Einstein tensor for the background metric equals 8 pi times t mu nu minus 1 over 8 pi g quadratic mu nu. This means we're extracting the low frequency part of the right hand side. And the other equation is the linearized Einstein tensor equals 8 pi times t mu nu minus 1 over 8 pi gq, and we extract the high frequency part. From these results, we have the key observations that the low frequency parts of the quadratic Einstein tensor and the stress energy momentum tensor produce curvature in the background spacetime. And for the high frequency components, recall that the linearized Einstein tensor is just the wave operator acting on the perturbation in the Lorentz gauge. So the high frequency parts of the quadratic Einstein tensor and the stress energy momentum tensor act as sources that modify the propagation of the gravitational waves. Recall that our goal is to identify and quantify the energy as well as momentum and stress carried by gravitational waves. Now we have our answer. The low frequency part of minus 1 over 8 pi times the quadratic terms in the Einstein tensor act as a source for the background curvature, just like the stress energy momentum in the matter fields. So the stress energy momentum tensor for the gravitational waves we'll denote by little t mu nu. That's minus 1 over 8 pi times the quadratic terms in the Einstein tensor, the low frequency part. And now the low frequency part of the Einstein equations can be written as g mu nu of g tilde equals 8 pi times the low frequency part of the matter stress energy momentum tensor plus the gravitational wave stress energy momentum tensor. Now recall that the Einstein tensor for any metric always satisfies the contracted Bianchi identity. So if we let del tilde denote the covariant derivative with respect to the background metric, so this is covariant derivative for g tilde, then the background Einstein tensor satisfies del tilde mu g mu nu of g tilde equals 0. And from the Einstein equations, this implies del tilde mu acting on the matter stress energy momentum tensor, the low frequency part, plus the gravitational stress energy momentum tensor equals 0. This result, if you'll recall the discussion of the stress energy momentum tensor from lecture number 22, is just the expression of local energy momentum conservation. In this case, the conserved quantity is not just the energy and momentum in the matter fields, but it's a combination of the energy and momentum in the matter fields and the gravitational waves. Now that we've identified the stress energy momentum tensor for the gravitational waves, we're left with the technical challenge of computing the quadratic terms in the expansion of the Einstein tensor. Recall the Einstein tensor for the full metric, g, can be written as big G mu nu of background g tilde plus perturbation h. And then this is expanded as the Einstein tensor for the background metric plus terms linear in the perturbation plus the term we're really interested in here is the quadratic term, the term quadratic in the perturbation. It will be useful to denote the Einstein tensor for the background metric as big G tilde. So what we're after is explicit expressions for the linear terms and the quadratic terms in this expansion. The calculation of these terms is long and complicated, so I'm just going to show you the answers and then outline the derivation. These are the linear terms. You'll notice each term is linear in the perturbation h. Del tilde is the covariant derivative with respect to the background metric, and you'll notice we have capital G tilde, that's the background Einstein tensor, this is the background Riemann tensor, and the background Ricci tensor. And of course in all of these terms, indices are raised and lowered using the background metric. Now let's look at the quadratic terms. Each term is quadratic in h. Del tilde is the covariant derivative with respect to the background metric. The Ricci tensor for the background metric occurs in a couple of places, and indices are raised and lowered with the background metric. We'll return to this expression in a minute and discuss how to extract the low frequency part to obtain the stress energy momentum tensor for the gravitational waves. But for now, I want to give some indication of how these results are derived. The first step is to relate the covariant derivative for the full metric to the covariant derivative for the background metric. So, for example, acting on a covector, W sub mu, this is equal to partial mu W nu minus gamma mu nu sigma W sigma, whereas this is equal to partial mu W nu minus the background Christoffel symbols. So these are the Christoffel symbols built from the background metric, times W sigma. Now these results tell us that del mu W nu minus del tilde mu W nu equals minus gamma sigma mu nu minus gamma tilde sigma mu nu times W sigma. Let's call this combination of Christoffel symbols C mu nu sigma. And now we have the result del mu W nu equals del mu tilde W nu minus C mu nu sigma W sigma. Recall that Christoffel symbols are not tensors, but whenever you take the difference of Christoffel symbols, the result transforms as a tensor. So C mu nu sigma is a type 1,2 tensor, and you can see that from this result, in which each of the other terms in this expression are tensors. And now we extend this relation between covariant derivatives to other types of tensors. For example, del mu acting on a contravariant vector v nu is equal to background del mu v nu plus c times mu nu sigma v sigma. For the next step, we use del mu g alpha beta equals 0 to show c mu nu alpha equals 1/2 g alpha beta times del tilde sub mu g nu beta plus del tilde sub nu g mu beta minus del tilde sub beta g mu nu. And now we use the following result for the Riemann tensor. R mu nu alpha upper beta wired together with a covector W sub beta is equal to del mu del nu W alpha minus del nu del mu W alpha. And next we use our previous results to replace the covariant derivatives with respect to the full metric with covariant derivatives with respect to the background metric. And this gives a result for the full Riemann tensor in terms of the background Riemann tensor and background derivatives of the metric. Next, we set g mu nu equal to the background plus a perturbation h mu nu. And this implies that g upper mu nu equals g tilde upper mu nu minus h mu nu plus h mu alpha h alpha nu. And then of course there are higher order terms, but we just need to keep terms through quadratic order in the perturbation h. And remember, indices are always raised and lowered with the background metric. And now using this result in our Riemann tensor, we find R mu nu alpha beta in terms of R tilde mu nu alpha beta, the background metric and the perturbation, and also derivatives of the perturbation. Del alpha h mu nu and del alpha del beta h mu nu. And of course here we just keep terms through quadratic order in h. And now that we have the Riemann tensor, we contract indices to obtain the Ricci tensor, curvature scalar, and the Einstein tensor. And of course, always keeping terms through quadratic order in h. In particular, this gives us the Einstein tensor, g mu nu of the full metric g in terms of the background geometry, and also h and its first and second derivatives. The result of this long and complicated calculation is what I've shown here. The leading order term in the Einstein tensor is just the Einstein tensor for the background metric. The linear terms are displayed right here, and the quadratic terms are displayed here. And remember, it's the low frequency or long wavelength part of the quadratic terms in the Einstein tensor that define the stress energy momentum tensor for the gravitational waves. Let me repeat the definition. We have T mu nu equals minus 1 over 8 pi times g quadratic mu nu. And we take the low frequency or long wavelength part. This is the stress energy momentum tensor for gravitational waves. And now that we know what GQ is, we're faced with the question, how do we extract the low frequency, long wavelength part? The answer is that we average GQ over a space-time region that is large compared to the high frequency short wavelength part and small compared to the low frequency long wavelength part. So the picture we have is a signal that contains both high and low frequency parts. So this is GQ mu nu. And what we're going to do is remove these high frequency ripples by averaging over a region that's large compared to the short wavelength part, but small compared to the long wavelength part. We'll use angle brackets to denote the averaging process. Then the gravitational wave stress energy momentum tensor becomes minus 1 over 8 pi times the average of the quadratic terms from the Einstein tensor. In taking the average, many of the terms in that long, complicated expression for GQ, many of those terms will vanish. And this can be shown in general, but I'm going to simplify the analysis by assuming that the background geometry is nearly flat. So in particular, we'll set G tilde mu nu equal to eta mu nu. Even though we had to allow for a more general background in order to identify the stress energy momentum tensor for the gravitational waves, now that we have this result, we can return to the assumption that the background is nearly flat and approximate G tilde by eta mu nu. So let's take a look at GQ once again. When we set G tilde equal to eta, then these background covariant derivatives, for example, this covariant derivative, just become ordinary partial derivatives. And these terms involving the background Ricci tensor vanish. Now notice that each of these remaining terms is of course quadratic in H, but also each term contains exactly two derivative symbols. So GQ with the background set equal to eta mu nu is a combination of terms of the form partial partial HH, partial H, and H times partial partial H. Now these terms can always be rewritten using integration by parts in the form partial of H partial H minus partial H partial H. So you can see that GQ can be expressed as a combination of terms, some of which are total derivatives, and the other terms are of the form partial H partial H. Now when we average GQ, all of these total derivative terms vanish. The way to see that is to note that what's in parentheses here contains two factors of H. So it contains a low frequency and high frequency part. So here's a piece of that signal. And here's the low frequency or long wavelength part. And this is the high frequency or short wavelength part. Now this high frequency short wavelength part of the signal is removed by the averaging procedure, which takes place in a window something like this. So the averaging removes this part, sets it equal to 0, and the derivative removes the low frequency long wavelength part. Remember, this window is very short compared to the long wavelength, so the function, the dot 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 here, is approximately constant. And the derivative of a constant is 0. So you can see from this argument that both the low and high frequency parts of a total derivative will average to 0. So when we extract the low frequency long wavelength part of GQ, the only terms that remain are minus 1/4 partial mu h bar alpha beta, this is the trace reversed metric perturbation, times partial nu h bar alpha beta, plus 1/8 partial mu h bar alpha alpha partial nu h bar beta beta, plus 1/4 times partial alpha h bar alpha beta times partial mu h bar beta nu plus partial nu h bar beta mu. Recall that the trace reversed metric perturbation, h bar, is just defined as the metric perturbation minus 1/2 eta times the trace. And now the stress energy momentum tensor is just minus 1 over 8 pi times this result. Now remember from the last lecture that we can always choose coordinates in which the metric perturbation satisfies the Lorentz gauge. That's partial mu h bar mu nu equals 0. In this case, the stress energy momentum tensor simplifies to 1 over 32 pi times the average of partial mu h bar alpha beta partial nu h bar alpha beta minus 1/2 partial mu h bar alpha alpha partial nu h bar beta beta. And finally, recall that for radiative solutions in vacuum regions, we can impose the transverse traceless, or TT gauge. In the TT gauge, H00 vanishes, as well as H0I. Here the index I ranges over 1, 2, 3, or XYZ. Also, the metric perturbation is trace-free and transverse. In this gauge, the stress energy momentum tensor for the gravitational waves is 1 over 32 pi times the average of partial mu Hij partial nu Hij. Let's finish with an example. A monochromatic plane wave in the TT gauge. In the last lecture, I showed that the metric perturbation is given by the real part of an amplitude Aij times the exponential of I times k vector dot x vector minus omega t. Here, k is the wave vector, and x vector is just xyz. Omega is the magnitude of k, and Aij is the amplitude, which is transverse and trace-free. If we introduce an orthonormal basis, E1i, E2i, and k hat I, so k hat is the unit vector in the direction of the wave vector k, so it's defined by ki over omega. With this notation, the amplitude can be written as A plus times E1i, E1j minus E2i, E2j, plus A cross times E1i, E2j, plus E2i, E1j. These two independent components of the amplitude define the plus and cross polarizations for the gravitational wave. Now let's compute the stress energy momentum tensor for this wave. We'll need to compute the derivatives of Hij with respect to t and xyz, and when we do that, we'll bring down a factor of either omega or k vector. In fact, it's easy to see that the derivative of Hij can be written as k mu times the real part of I times Aij e to the I k dot x minus omega t. And here, the space-time wave vector, k upper mu, just has its time component as omega, and its spatial components are k vector. The index here is lowered with the flat-Minkowski metric, and that just puts an extra minus sign into the time component. And of course we're assuming that the space-time wave vector is real, so that allows us to bring k mu outside of the real part of this expression. And now simplifying, we have partial mu hij equals k mu times minus the real part of aij times the imaginary part of the exponential, which is sine of k dot x minus omega t, minus the imaginary part of aij times the real part of the exponential, which is cosine k dot x minus omega t. For the stress energy momentum tensor, we need to compute partial mu hij partial nu hij, and that will equal k mu times k nu times the square of this factor, which is the real part of aij times the real part of aij times two factors of sine, so sine squared of k dot x minus omega t, plus imaginary part of aij times imaginary part of aij times cosine squared of kx minus omega t, and then the cross terms give 2 times the real part of aij times the imaginary part of aij times sine of kx minus omega t times cosine of kx minus omega t. The next step in computing the stress energy momentum tensor is to take a space-time average over several wavelengths and several time periods. Now the average values of sine squared and cosine squared are both 1/2, but the average value of sine times cosine is 0. So the average value of this expression is 1/2 times k mu times k nu times the real part of aij squared plus the imaginary part squared. And now we can insert our expression for the amplitude in terms of the plus and cross polarizations, which is right here. And for notational simplicity, let's let this combination of basis vectors be denoted Eij plus, and this combination will denote by Eij cross. So returning to our result here, we want to insert Aij equals A plus times Eij plus A cross times Eij cross. And we'll use the following results, which are straightforward to verify. Eij plus is equal to 2, as well as Eij cross, and Eij plus Eij cross is equal to 0. Then, for example, the real part of Aij times the real part of Aij is equal to the real part of A plus times E plus the real part of A cross times E cross, all of that times the same thing. And this simplifies to 2 times the real part of A plus squared plus 2 times the real part of A cross squared. Likewise, this term gives 2 times the imaginary part of A plus squared plus 2 times the imaginary part of A cross squared. Then this result becomes the average of partial mu hij partial nu hij is equal to k mu k nu times the complex magnitude of A plus squared. So that's the real part of A plus squared plus the imaginary part of A plus squared plus the complex magnitude of A cross squared. So our final result for the stress, energy, and momentum tensor of a plane monochromatic gravitational wave is T mu nu equals 1 over 32 pi times K mu K nu times the squared amplitude of the plus polarization plus the squared amplitude of the cross polarization.